Greetings from the Department of ECE. Welcome to module number 4. So in this module, we'll be learning about various logic styles available, and we'll be designing how to design various logics, various basic logic gates using each and every logic design style. So first, let us understand what are the various logic styles available, and then we'll design some basic gates and circuits using every logic design style. And finally, we'll be learning to design some basic adder and multiplier blocks. So these are the different logic styles that are available, and that there are many logic styles available. So in this unit, as per your syllabus, we'll be seeing some of those. We'll be analyzing what is CMOS static logic. This CMOS static we have already seen in switch level modeling. When you design the basic gates for switch level modeling, you use CMOS static logic, that is ratioless. You have ratioed as pseudo NMOS. So static circuits are designed using CMOS static logic, and the following three are switch logic, that is transmission gate, pass transistor. So a transmission gate and pass transistor itself can act as a tri-state, and tri-state, what is meant by tri-state, we'll be seeing in that also. And we have dynamic, that is for dynamic circuits or circuits involving uh, uh, value. When you go for combinational or when you go for static circuits, it is just a variable value. When you go for dynamic circuits, your register and your a value that is stored, okay, for a particular time period comes into picture. Okay, dynamic circuits can be designed using dynamic domino KSPC circuits with clock, okay, that is synchronous circuits. And you have separate, that is NORA, no race condition, and DCVS, differential cascade voltage switch logic. So before going into the logic design style, CMOS logic design style, which is very simple. Okay, so we'll be seeing how an NMOS and PMOS behave. When will an NMOS turn on? NMOS will turn on for a high value. Whenever I feed an NMOS with a logic 1 or a high value, my NMOS will turn on. To sustain an NMOS, to make NMOS remain in on condition, I should satisfy this rule, that is VGS is greater than VTM. Similarly, my PMOS will turn on for a lower value, that is 0. What should I do to sustain this PMOS in on condition? My VSG must be always greater than mod VTP. Why it is VSG? Because source is tied to VDD. Okay, so this will be taken as VSG, but here it is VGS. The reason is source is tied to ground, lower level. Okay, and here for a PMOS, threshold will be negative, so I'm considering mod of VTP. Okay, so this is the condition for sustaining your PMOS in on condition. Okay, NMOS will be in on, or it act like a closed switch when you give a high input. Okay, if it will be in off when it is low. Similarly, PMOS on when you give a low voltage, PMOS off when you give a high voltage. Okay, and in case of static logic and CMOS static logic design cell, you must understand that PMOS and NMOS cannot be on at the same time. Okay, it is not possible. That is, if you consider static any gate designed using static logic style, for the same input, both NMOS and PMOS cannot be in on condition. Okay, different inputs corresponding different NMOS and PMOS can be simultaneously on. Same input, if it is given to an NMOS and PMOS, both NMOS and PMOS will not be in on condition. It is not possible. Your input can either be 0 or 1. Okay, 0 means only PMOS will turn on. 1 means only NMOS will be turning on. And this is your circuit structure of your CMOS static logic. You have a pull up network, you have a pull down network. Pull up network அப்படினா PMOS, pull down network now NMOS. Why it is a pull up network? Because it pulls up the output from via VDD. Why it is called as pull down network? Because NMOS always drains all the voltages to ground. Okay, depending upon the logic, you are going to give the number of inputs and choose the number of transistors. If it is 2 input AND gate, in 1, in 2, and 2 PMOS will be here. If it is two input, yes, if it is two input AND gate, you will have two NMOS transistors over here. And your CMOS static logic, which is very basic one, it is a ratioless logic. Okay, there is no proper ratio that is sustained between this pull up and pull down network. No sizing ratio is maintained between pull up and pull down network. And if you uh, don't have any control parameter, okay, so why did I include this point is உங்களுக்கு வந்து சைசிங் யூஸ் பண்ணி உங்களால் ஒரு சில பேராமீட்டர்ஸை பெர்ஃபார்மன்ஸ் பேராமீட்டர்ஸை கண்ட்ரோல் பண்ண முடியும். இது வந்து சைசிங் ரேஷியோ இல்லாமல் டிசைன் பண்ணியிருக்கீங்க. ஸோ இன்ஸ்டெட் ஆஃப் கான்சென்ட்ரேட்டிங் ஆன் சைசிங் ரேஷியோ, மை பெர்ஃபார்மன்ஸ் கேன் பி இம்ப்ரூவ்ட் பை any other change also. So here I have mentioned that supply voltage scaling is one such possible way. Okay, and it has an n block and p block. So p block is pull up and n block is pull down network. Okay, so if your input is n, you have 2n number of transistors. That means if your input is 2, you have 4 transistors. If your input is 4, you have 8 transistors. Okay, and at any instant you have the gates or the entire logic connected to either VDD or ground via a load resistance path. That is, your output is either 0 or 1. இல்லையா? 0 எப்படி கிடைக்கும்? உங்களுக்கு பாத் வந்து அவுட்புட்ல இருந்து கிரவுண்டுக்கு இருந்தால் தான் 0 கிடைக்கும். அதே மாதிரி 1 எப்படி கிடைக்கும்? VDDல இருந்து பாத் இருந்தால் தான் 1 கிடைக்கும். So at any point, at any instant, each gate output is connected to either VDD or ground. Only if you have path, low resistance path, ஏதாவது ஒரு PMOS NMOS ஆன் ஆயிருக்கும், அது வழியா உங்களுக்கு it will remain as a closed switch. So you have a path from VDD to output, or you have a path from output to ground via any transistor with respect to your logic. Okay, so at any steady state, you don't have both pull up network and pull down network. Entire pull up network and pull down network cannot conduct at the same time. And very important, you must understand that complementary MOS will always give a complementary output. It will not give a true output. Any design that is implemented in CMOS static logic will not give a true output. It will give only a complementary output. If you want a true output to be obtained, always add an inverter at the output terminal. So now we'll see ratioed logic, that is pseudo NMOS logic. So here I have replaced my pull-up network, that is PMOS circuitry, with a single PMOS connected to ground. That is, this PMOS will always be in on condition, that is in linear state. So this will act as a resistance or a load. Okay, and similar to your CMOS static logic, here I will have the NMOS transistors, that is pull-down network. Instead of using PMOS transistors, replace the entire network with a single PMOS transistor connected to ground. So what is the advantage, or what is different in case of CMOS static ratioed logic? So ratioed logic la, pseudo NMOS logic la, உங்களுக்கு வந்து you will maintain a proper sizing ratio between your pull up network and pull down network. அப்படின்னா உங்களோட single PMOSக்கும் கீழே இருக்கிற NMOS transistors-க்கும் you will maintain a sizing ratio, that is W by L ratio. Okay, so in the last unit you would have seen derivation NMOS inverter driven by another NMOS inverter. So based on that derivation, your ZPU by ZPD is chosen as 3 by 1. That is, W by L ratio of pull up network by W by L ratio of pull down network has to be 3 by 1. Okay, so ZPU is LPU by WPU. ZPD is the LPD by WPD. Okay, so what is the disadvantage here? Here now you consider this inverter itself. Suppose my input is 1 here, my NMOS will turn on, but my PMOS will be in always in on condition. So there is a path from VDD to ground. Okay, so you have a path from VDD to ground. So static state, at any static state, you have power moving from this VDD to ground. So static power consumption is more in case of pseudo NMOS logic. Okay, so here you have seen a 4 input AND gate designed using pseudo NMOS logic. Advantages, you have minimum number of transistors. So in case of CMOS static logic, this is the basic inverter. You have this truth table. Okay, so whenever you have a 1, NMOS turns on, PMOS will remain in off condition. So PMOS will remain in off condition. So you have path from, this is on, so this is acting as a closed switch, path from V out to ground. Even if there is some minimum voltage present here, everything will move from output to ground. Okay, so what happens when you give a 0? Your PMOS will turn on. Okay, so this will be in, on condition. Okay, so this will be in on condition. You have a path from VDD to output, so you have a higher output, that is 1. Similarly, let us understand what happens in AND, that is NAND. Okay, so we have seen a complementary MOS static logic will always be used for implementing a complementary output. Here I'll get only NAND. If I want to AND, I have to add an inverter here. Fine. So let me check what happens when I give a 0 0. Okay, so here also it is 0, here it is 0, here it is 0, here it is 0. PMOS turns on for a 0. So this, you have a path from VDD to output. Here also you have a path from VDD to output. So my output is 1. Okay. Next combination is 0 and 1. So A is 0. Okay. Here also A I have given a 0. B is 1. Here it is 1. Here it is 1. Okay. So if it is 1, this transistor will turn on. This transistor will turn off. Okay. What about here? Here I have my B as 1, A as 0. Okay, so my A transistor will turn on. Okay, so now here I have a path from VDD to output. Again, my output is 1. Why here I don't have any draining of output? This transistor is an off condition. So இது வந்து close switch act பண்ணாது, open switch இருக்கும். இங்க இருந்து இந்த நோடு வரைக்கும் வரதுக்கு there is no path, but this transistor is in on condition. Okay, so even though this is on, this is in off condition, so you don't have path from output to VSS. Okay, so now next let me analyze. Okay, next I have 1 and 0. A is 1, B is 0. A is 1, B is 0. Okay, so what happens when my A is 1 and B is 0? This transistor is in on condition. This transistor is in on condition. Similarly, here I have a path from VDD to output, so the output is high. I have obtained. Here, practically speaking, my 1 will not be obtained as output. You have little degradation in your output, practically speaking. The reason is this transistor is in on condition, so if it is 5 volt, at least 1 volt will have a will be leaked out of this node till this point. Okay, only till this point, because again B transistor is a open switch, it will not move any voltage from here. Okay, so finally what happens when both are 1? So if both are 1, obviously both the PMOS will remain in off condition, both the NMOS will remain in on condition. Whatever nodal voltage present at this node is moving to ground. Okay, so one of the basic things you must remember is, whenever I want to design a dot product A dot B. Okay, so AB is not possible, AB bar is possible in case of complementary MOS static logic design. But hope you know the basics. If you wanted to design dot product, if you want to design A dot B, then NMOS has to be in series and PMOS has to be in parallel, and vice versa for OR gate. So you can see this OR gate, your PMOS is in series and NMOS is in parallel. So now let us check to the truth table for this also. Okay, now first combination. A is 0, B is 0. Okay, so both the zeros will turn on my both CMOS. Both of this will remain in off condition. So you have a path from supply to output. My output is 1. What about my next combination? A is 0, B is 1. Okay, so if B is 1, A is 0, so this remains in on condition. B is 1, so you have this transistor as an on condition. Okay, so here you have NMOS in parallel. So from your output node there is path to ground. So across Y this transistor is closed, so you have a path to ground. So 0 is obtained. Similarly, when you see this PMOS, they are in series. இது ஆன்ல இருந்தாலும் இது ஆஃப்ல இருக்கும். அப்போ VDD வந்து இங்க இருந்து இது வரைக்கும் தான் வர முடியும். After this you have a open switch, you cannot pass the high voltage. Okay, likewise what happens when you give a 1 and 0? So you have 1 and 0. Okay, so this will remain in on condition, again off condition. A will turn on a transistor, so this will remain in on condition, this will remain in off. So since the NMOS is in parallel, if any one of the NMOS is in conducting state, remove the voltage that is available or output node to ground. So again 0. Okay, so what happens when both are 1? If you have 1 and both, you make your both NMOS to turn on, and your PMOS will, both the PMOS will remain in off condition. Okay, so both the PMOS in off condition, both the NMOS in on condition, all the voltage present at the output will move to ground. We will see some of the advantages and disadvantages. So one of the main advantages, low static power consumption and uh, good noise margin. Okay, so why good noise margin? So we have already you would have already learned what is noise margin. You would have learned what is VIL, VIH, VOH, VOL. In case of static CMOS static logic, VOH and VOL. Okay, so VOH is nothing but that is voltage output high. Okay, the minimum value of high voltage will be always ideally equal to VDD, and VOL will be ideally equal to 0. So this minor degradation only happens in case of practical analysis. Okay, so the noise margin will be very good, and a low static power consumption. When compared to ratioed logic, you have very less static power consumption because you don't have a path from VDD to ground at any instant. You will not have direct path from supply to ground. Whenever you have direct path from supply to ground, when any input is forced, that is static power consumption. Okay, but here in this case, you don't have any such condition, and it is fast and it is easy to design. Okay, but what is the disadvantage? More number of transistors. So this disadvantage you can justify when you learn about all the logic styles. You can when you learn about dynamic, domino, and when you go for other logic design steps, you will understand that CMOS is taking more number of transistors. So that's all about your uh, CMOS static logic. Greetings from the Department of ECE. In this video, we'll be learning about transmission gate logic. These are the different logic styles we have seen. Logic styles available. We have already studied what is CMOS static logic. Now we are into transmission gate logic. So one of the switch logic. In this circuit, we'll analyze what is the circuit and the symbol used for transmission gate logic. So this is a circuit. So you have parallel combination of PMOS as well as NMOS, and you are controlling this transmission gate logic using the complementary control signals given to the gate. Okay, so you have S and S bar given to the gate of both NMOS and PMOS. So S and S bar are the control signals, complementary control signals. And what is the input? Input is X and output is Y. So when depending upon the control signal value, my any one of the transistor will be in on condition, and X will pass across the uh, transmission gate to move to Y. Okay, so this is a switch logic. parallel combination of NMOS and PMOS. You control this logic by complementary control signals. What happens when S is equal to 0? This will be in off condition. S is equal to 1, again S bar is equal to 1, this will be in off condition. So if both are in off, no path from input to output, so it is high impedance state. If S is equal to 1, what happens? Both here also it will be on, NMOS also turns on and PMOS also turns on. So depending upon the value of X, 0 or 1, the transistor will be chosen. Okay, so for example, NMOS is good at passing a strong 0, PMOS is good at passing a strong 1. Depending upon 0 or 1 and low resistance path, your input will move from X to Y. So now we know that NMOS can pass a strong 0 and weak 1. PMOS can pass strong 1 but a weak 0. Okay, so pass transistor, because of this property, you cannot design or you cannot use it for a higher level logics or higher designing bigger circuits. Okay, if you see the pass transistor video, you will understand why NMOS is good at passing a strong 0 and weak 1, and about this PMOS pass characteristics. Okay, so it is one of the main disadvantage in case of PTL logic. But in case of this transmission gate logic, you incorporate both NMOS and PMOS in a single circuit. So my entire transmission gate logic can pass both good 0 and 1, that is strong 0 and strong 1, because I have both PMOS and NMOS in the same circuit. Now if I have 1, here I have 0. Okay, so my NMOS will be in on condition and my PMOS also will be in on condition, so my output will be high. Okay, so your PMOS will be chosen for passing a 1. Okay, since it is good at passing a strong 1, your PMOS is always chosen. Okay, I told you in the last slide, you have both the transistors on, low resistance path will be chosen. Okay, so my PMOS will be chosen for passing a or will for passing a 1 or for conducting a 1 high value. And now if I have 0, my NMOS will be chosen because it is good at passing a good 0 or a strong 0. Okay, so what happens when my control signal is 0? A bar is 1 and A is 0. Both the transistor will remain in off condition. There is no path across this transmission gate logic, and whenever there is no path, it is called as floating state or high impedance. Okay, so this is the truth table for transmission gate logic. So you have control signal, you have input and output. Okay, so from the table I can understand that output has 0, 1 and Z. So this can act as a tri-state buffer. Now we'll see how to design a 2x1 multiplexer using a transmission gate logic. So this is the block diagram. You have two inputs P0 and P1. Depending upon the select line, either P0 or P1 will be chosen. So this is the equation: F is equal to P0 S bar plus P1 S. And this is how you implement 2x1 mux using transmission gates. Two transmission gates are being employed. Okay, so one input is given to one transmission gate, at another input is given to another transmission gate, and you can see the uh, position of control signals, S and S bar, and here also you have given S bar and S. Okay, so let us check how does it work. Now I have given SS1. What happens if S is 1? S bar is 0. Okay, so which transmission gate will have a path now? If S is 1, so you can see the bubble. The bubble represents your PMOS. Okay, without bubble, then it is called as NMOS. So you can understand that 1 given to NMOS will make NMOS on, 0 given to PMOS will make PMOS on. Okay, but you can see in this case, 1 given to PMOS off condition, 0 given to NMOS off condition. So this transmission gate will turn on, and you have a path for P1 to go across this transmission gate to F. Okay, likewise. Okay, so P1 has the path to reach F. Okay, likewise, what happens when you have a 0? S is equal to 0. If S is 0, here also I have 0 and here I have 1. Okay, so now you can see, you can check which will remain and which will turn on. So the transmission gate with P0 will turn on. The reason is, if you give a low voltage, PMOS will turn on. So one with a bubble is passed is given with 0, and here 1 is given to the NMOS. So this transmission gate TG0 will be in on condition. Okay, so now P0 has the path to reach F. Okay, so depending upon the control signals S and S bar, I can either make P0 to pass or P1 to pass through. Okay, so as already I have told you, P0 and P1 can either be 0 or 1. If it is 0, okay, corresponding transistor which is good at passing a strong 1 will be chosen, 0 will be chosen. If it is 1, the transistor which is good at passing a strong 1 will be chosen, okay, or low resistance path will be taken. So now let us analyze how XOR gate is designed using transmission gate logic. So this is the truth table. For similar inputs, I get a 0. For different kind of input bits, I get 1. So this is one way of designing how you can design XOR gate using transmission gate logic. Two transmission gates are used. You have two transmission gates. Uh, and what are the control signals? Here the control signal is A and A bar. Input is B and B bar. Okay. You have control signals A and A bar. Okay, they are tied to the NMOS and PMOS gates. And you have input as B and B bar. So now let us check how it responds for each and every input combination. First, let me check for 0 0 combination. A is 0, A bar can be 1. B is 0, B bar will be 1. So now let me check which transistor will turn on. Now A bar is 1. So A bar 1, 1 can turn on a NMOS. Okay, so this NMOS will turn on. Obviously PMOS will be in off condition. Okay, and A is 0, so again 0 will turn on a PMOS. So this, okay, this transmission gate is on now. Fine, this transmission gate is on. Now I have 0 here, so there is a path for 0 to move from B to F. So my output is 0 again. Fine. Next is A0 B1. I have to change the value of B now. Okay, now I have B as 1, so B bar will be 0. But my A is 0, so the same transmission gate will remain in on condition, but the value alone will differ because this B has the path to move from here to F. So 1 will pass from B to F. 1. Okay. Next condition 1 0. A is 1. Obviously, if A is 1, A bar will be 0. Now, since the control signal has changed, your transmission gate, second transmission gate will turn on. Okay, so this transmission gate will be turning on. Okay, so now let me check again. So 1 0 combination. My A is 1, okay, and A bar is 0, and B is 0. If B is 0, here B bar is 1. So 1 has the path to move from B bar to F. 1. Okay, last combination 1 and 1. A is 1, A bar is 0, B is 1, B bar is 0. Okay, so again this transmission gate is an on condition, but 0 here. So 0 will have the path to move from this position to F. So this is how I design, I have justified your truth table. So in this we will see some of the plus and minus points of transmission gate logic. So as we know already, there is no VT effect or threshold degradation over here. You get a strong 1 and strong 0 as the output. Okay, because you have both NMOS and PMOS coming to the picture. You have both You have no degradation in your outputs, and it is more complex and it is taking more area. Why it is more complex? You have both NMOS and PMOS as in parallel connection. So in case of designing as well as in fab, you have a little complexity here. Why you have complexity in fabricating? You have to consider both NMOS and PMOS in parallel connection. Okay, so fabricating both in the same, it will take more fab problems. Okay, complexity is there in fabricating. More area. Okay, compared to fast transistor. At another switch logic, here you have more transistors coming into picture. For example, XOR gate you have designed using fast transistor also. It requires only one to two transistors. Here I have four transistors, so area is more. And one of the points here, which cannot be sounding as a great problem, but it is a problem when you design and when you fab it. That is, it requires true and complement of gate signal. So whenever I design the very big system or a very big circuit using transmission gate logic, it is my duty to give both true and complement as a control signal. So if you when you see the generation of VDD supply and clock lines, now when you're studying, you have seen it as just as a 1 and 0, but generation of clock, generation of true and complement of signal requires separate circuitry. So this is in turn yet another problem or yet another complexity faced when you design any circuit using transmission gate. Greetings from the Department of ECE. In this video, we will be learning about fast transistor logic. So these are the various logic cells available. So so far we have seen what is static logic and transmission gate. Now we'll move towards PTL. Before moving into logic design using fast transistors, first let us analyze how an NMOS act as a fast transistor and PMOS act as a fast transistor, and then we'll see some properties or features of PTL logic, and then we'll see some of the examples, that is AND and OR gate I have given here, that is AND and OR logic designed using fast transistor logic cell. Finally, we'll be going through some advantages and disadvantages, plus and minus of this logic. Now we'll analyze why NMOS can pass a strong 0 and a weak 1. Before moving into that, we'll first understand if we use an NMOS as a pass transistor, how does it pass the value? And if you see the diagram, you will understand. So here I have an NMOS transistor used as a pass transistor. So உங்களோட control voltage, it will be given to the gate and the input will be passed across source to drain and drain to source. Both ways are possible. Whenever a transistor is used as a pass transistor, NMOS or PMOS, current conduction from source to drain and drain to source is possible. Now I am going to justify why NMOS is good at passing a strong 0 but a weak 1. So some of the basic things we'll recap. In case of digital, if it is a high voltage, it is logic 1, low அப்படினா 0 volt. So we in case of analog, we'll see VDD will be the high and 0 volt will be the low. And what is the condition for NMOS to turn on? That is, whenever you give NMOS a higher value, logic 1 across the gate, your NMOS will turn on. What is the condition to make the transistor sustain in linear region or sustain in a on state? VGS greater than or equal to VTN. If your VGS is greater than threshold or equal to threshold, your transistor remains in on condition. Okay, and since we are going to analyze across the terminals, you must understand VGS is equal to VG minus VS. Why VG minus VS? In case of any NMOS, your source will be tied to ground, so you must include VG minus VS. இதே PMOS எடுத்துக்கிட்டீங்கன்னா, you will be declaring it as VSG, VS minus VG. The reason is the source of PMOS is always tied to higher level, that is VDD. Okay, so for analyzing this justification, I am going to consider my threshold as 2 volt and higher voltage or VDD as 5 volt. So first let me let me start from lower voltage, and I have given a control voltage of 5 or high, that is VDD. Now what happens when I give a 2 volt? I get a 2 volt again. How do I get a 2 volt? Whenever I'm giving a high volt, this transistor is in on condition. And what is VGS? So VG is 5, VS is 2. VGS is VG minus VS. That is 5 minus 2, 3 volt. 3 volt is greater than the threshold of 2 volt. So it is an on, it remains in on condition and it will pass the value of 2 volt across source to drain. Next I'm going to give 3 volt. Again 5 minus 3 will give me 2. Now also it is equal to threshold. So my transistor remains in on condition. It is sustained in on condition. So my output will be 3 volt. Now let me increase to 5 volt. If I increase to 5 volt, here also I have given 5, here also I have given 5. Vg minus Vs will be 0. So now my transistor will be in off condition. It cannot pass the value from here to here. The already available or retained value of 3 volt will be present here. So my transistor, NMOS transistor, has failed in passing a high value. So when if you consider the value that is given across the source, okay. So for example, I have taken the VT as 1 volt and VT as 5 volt. If I'm increasing linearly, that is from 2.1, 2.2, right, from each and every voltage, if I'm considering till 5 volt, if I analyze, I'll be getting the voltage here as VDD minus VTN. Whenever I give a high, I'll be getting a 4 here. If my threshold is 1. So here I have retained this 3 volt. Okay, that is 5 minus 2 is 3. So I am getting a 3 volt here. Okay, so my NMOS cannot pass a strong 1. It can pass only a weak 1. Okay, so pass transistor it can conduct in both directions. ஸோ இப்போ இங்கே இந்த இடத்துல ட்ரெயின் இந்த இடத்துல சோர்ஸ்னு கன்சிடர் பண்ணீங்கன்னா இந்த இந்த ஜஸ்டிஃபிகேஷன் அப்படியே ஆப்போசிட்ல பண்ணியிருப்பாங்க. லெட் இஸ் வாட் ஷுட் ஐ டூ டு sustain or to obtain the condition VDD minus VTN at drain. In that way they would have derived and they would have obtained the condition also. Okay, so they will justify that whenever my VGS, that is at drain terminal, whenever it is going beyond VDD minus VTN, the transistor will remain in off condition. Okay, so now on the whole my NMOS will not pass a strong 1, it will pass only a strong 0. Similarly, why PMOS passes a strong 1 but a weak 0? Similar kind of analysis we are going to do. Here also you can pass the value from source to drain and drain to source. So PMOS, same kind of conditions. So VDD high and 0 volt is low. So when will a PMOS turn on? For a lower value. 0 volt கொடுத்தீங்கன்னா PMOS வந்து onல இருக்கும். And to sustain or to make PMOS remain in the on state, you must satisfy the condition VSG is greater than or equal to modulus of VTP. Why modulus of VTP? Your threshold will be negative in case of PMOS. So, and what is VSG? VS minus VG. Okay, so why VS minus VG? In any PMOS, your source will be always tied to VDD, that is source at higher level. So VS minus VG. I am considering my threshold as minus 2 volt here and VDD as 5 volt here. Same kind of analysis. So what happens if I give a 3 volt? Again, I am giving a 3 volt here since my transistor is on. Here it is 0. So 0 VS minus VG. 3 minus 0 will give 3. Okay, so 3 is greater than mod of VTP. 3 is greater than 2 volt. So my transistor is in on condition. Passing of 3 from source to drain happens. Now I am giving a 2 volt. 2 minus 0 will be equal to 2. Threshold is also 2. So VSG greater than or equal to mod of VTP. Satisfied. So it still remains in on condition. So my transistor is in closed circuit state. It conducts. Now I am giving a 0 volt. What happens? 0 minus 0, 0. So it is not greater than mod of VTP. This transistor will be in off condition now. So it will not pass the value of 0 here, but already retained value 2 volt will be obtained as the output. So exact 0 will not be obtained, but a little higher voltage will always be obtained. So it is a weak 0. If it is a perfect 0, it has to be 0 volt, but you can get from 0 to 2 volt. Okay. Similarly, here also your PMOS could not pass a low value. It could pass the low value as one threshold. Okay, so one threshold which is retained is obtained here. So now we'll see some of the features or characteristics of fast transistor logic. So this is a switch logic or relay logic, and it is suitable only for small array applications. So you have some drawbacks in fast transistor. So it can be used only for smaller logic. Okay, you cannot design bigger circuits or bigger logic using this logic set. And as I told you earlier, as you have seen earlier, current conduction in both directions is possible. And one of the unique points is you can use the primary inputs to as a control signal as well as giving as an input to the source or drain terminals. Okay, so this is possible only in case of PTL. In no other logic, the primary inputs will be used as a control as well as an input. And in PTL, you conventionally use the any transistor NMOS or PMOS to pass both 1 and 0. Uh, Even though we have seen that NMOS is good at passing only a strong 0 and PMOS is good at only passing a strong 1. Uh, if you want to design a logic, you have to use the pass transistor to pass both high and low voltage. And one of the main advantage here is there is no static power consumption, no static current from supply lines. So you don't have path from VDD. So you don't have any static current. So this is a pass transistor. So your B is a control signal. A, okay, you have as A as input and X as the output. And with the N channel transistor, high voltages will be degraded by 1 threshold, which you have seen in the first slide when we are justifying why it cannot pass a strong one. So this pulling down of high voltage. So whenever I give a high voltage, it will be degraded by 1 threshold. So this will get further worsened, or this will get uh, 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 further spoil the actual working when you have more body effect in your circuit. Okay, so this is called as VT effect. One of the major disadvantage of your pass transistor logic. So this will lead to one of the minus point of your PTL logic. That is, you cannot use more than one pass transistor to drive another pass transistor. So one pass transistor can drive only one or two pass transistors. More than that, it cannot drive. Okay, so that is why you use only for a small array applications or smaller logic applications. And your this degradation of your output, when you pass a high voltage, you will not get a high voltage. If you want to obtain the high voltage, your full logic levels can be obtained by or restored with the help of an inverter at the output of a gate. Fine. And whenever I give a input 0 0 0 0 1 1 0 1 1, so what happens whenever I give a 0 here and 0 here, there is no path. The switch is off condition. So high impedance state. Whenever there is no path, it is a high impedance state or floating state. So I have output as 0, 1 and Z. So it can act as a stray state also. So now we are going to see AND and OR gate logic using pass transistor logic style. Okay, so this is the truth table for AND and OR logic. And this is a circuit that is used. So if you are clear with the pass transistor design, okay, you can design a same gate, you can design a same logic in various different styles. If you are thorough with actual working of PMOS and NMOS pass transistor, it is very easy, and it is very you can enjoy designing various logics. Okay, so one way, I cannot say this is actual circuit, one way of designing an AND gate using pass transistor is this circuit, and one way of designing OR gate using PTL is this circuit. So now let me check what happens if I force all these input sets. First 0 0 combination. So A is 0 and B is also 0. If B is 0, B bar is 1. Okay, so what happens? Which transistor will turn on? NMOS will turn on for a higher value. So my 0 will be obtained as the output. I have obtained. Okay, now 0. And now 0, 1 condition. Okay, so A is 0, B is 1. If B is 1, what about B bar? 0. Now which transistor will remain and will turn on? Here I have a 1, that is high voltage. So this transistor will turn on. So what is A again? 0. So 0 will be obtained as the output. Okay. Now 1, and let me consider B as 0. So if it is 0, 1 here. So this transistor will remain on and 0 will be passed across this transistor. Again I get a 0. Now again here I have 1. Let me consider B also 1. So A is 1, B is also 1. So this transistor will turn on, and across this transistor there will be passing of 1 to F. Now I get a 1. So this is the AND logic. Now what about OR? First 0 0 combination. 0 for A, B also 0. If B is 0, B bar is 1. So now NMOS will turn on for a B bar transistor. So this transistor will remain on and 0 will pass across this. So here I will obtain my value 0. Now next, A is 0, B is 1. 0 1 combination. Okay, so if B is 1, what about B bar? B bar will be 0. So this transistor will turn on for a higher value. So 1 will pass across this. This will act as a glow switch. Pass across this to F. I obtain a 1. Now next, A is 1. Okay, so A1, B0. A is 1, B0. B0 அப்படினா B bar 1. So this transistor will turn on, and the 1 across this, the 1 will pass across this to F. I obtain a 1 again. Now next, 1 1 value. My A is 1 and consider B as 1. Okay, so here my this transistor B transistor will turn on, and again here I have a 1. So it will pass across this line to F. So again I get a 1 value. So this is how you design an OR and AND logic. As I told you earlier, you can have n number of uh, circuits to design AND or OR. That is, different forms of PTLS can be obtained. You can just play with NMOS and PMOS pass transistors if you are thorough with the basic working. And let me point out some plus and minus points of your PTL logic. So here I can have a better layout. Why I can have a better layout? It is simple NMOS and PMOS transistors. So if I use NMOS, so previously I have seen AND and OR logic using NMOS pass transistors. All are NMOS pass transistors. Similar substrate, okay, or similar well, you can group all the transistors together. Okay, and you have reduced static power consumption. Why you have reduced static power consumption? No path from VDD to ground. You don't have any transistor connected directly to VDD always. Remember, you have not connected any transistor to supply always. Okay, so and you have less area and less complexity in fab. Okay, less complexity in fab compared to other switch logic. In case of transmission logic, you will have both NMOS and PMOS connected in parallel, which will create more complexity in fab. And what is the disadvantage? You have VT effect, that is degrading of threshold. Because of this VT effect, you cannot use a pass transistor to drive more than one or two pass transistor. Okay, so you can, it is limited to you using this for very small logic designs. So that's all about your pass transistor. Greetings from the Department of ECE. In this video, we are going to see about dynamic CMOS logic. So we have various dynamic logic circuits. Uh, so basic dynamic logic design style we'll see in this video, and then we'll see about various other dynamic circuit design, domino, NORA, DCDS. So all these are clock based or synchronous circuit design logic styles. And before moving into basic dynamic logic design style, we must understand why should we prefer dynamic logic more than static logic. So static logic compared to static logic, you will have less area, more speed, and less power. When you see each and every dynamic design style, you will understand that. In short, less area means the number of transistors used will be reduced when compared to static CMOS, and the speed, you have capacitance coming into picture in case of dynamic logic, because every dynamic circuit is dependent upon, or is actually running based upon the temporarily stored values. Okay, and this capacitance charging and discharging decides the speed. Okay, so in such a way you can design the capacitance to make sure that your speed is high, that is charging and discharging time is more faster. Okay, and you have less power also, because in case of static CMOS, static power consumption is one of the major drawback. That is, you have path from supply to ground. Even when your input is not evaluated, that is, if you, even if you don't, even if after you have forced your inputs, you will have a time period where power will be wasted from through the path from VDD to ground. That will not happen over here. This is the block diagram in which you're going to design your dynamic CMOS. You have two transistors, MP pre-charge transistor, ME evaluation transistor, both of which are fed by a clock, and you have a pull-down network. Your logic will be designed via this pull-down network, and in your output, I'll be having a load capacitance. Okay, so this load capacitance, it's a combination of every other capacitance of your MOSFET and the wiring capacitance. Everything is included over here. So the logic function you can implement in pull-down network or NMOS network. Okay, and the construction or the way in which you design is same as static CMOS. That is, if you want A dot B, go for NMOS in series and PMOS in parallel. If you want A plus B, go for NMOS in parallel and PMOS in series. And the number of transistors required, MP, ME. So these two transistors are default. Apart from that, depending upon the number of inputs, my number of transistors also will be required. So if n inputs are there, if 3 inputs, 3 transistors. So n input means n transistors. So n plus these two transistors, so n plus 2. So it is very less, that is, it is less compared to your static CMOS, and it is a non-ratioed one, so you need not maintain the sizing ratio between pull-up and pull-down network, and you need not maintain a proper ratio of W by L, but you have an option over here, that is for improvisation of your circuit performance. If you want good performance, go for changing the size of this MP to improve my transition time. Okay. So the size of this transistor can be made larger, W by L ratio. With respect to this, you can make this more larger than this NMOS used in the pull-down network. For what purpose? To improve the transition time. Which transition? You have two transitions, 0 to 1 and 1 to 0. So 0 to 1 transition time, if you want to improve, I can increase the size of this transistor. Okay. You will understand why it is required later. And here I don't have any power from moving a power going from VDD to ground, so static power consumption is missing. And why faster switching speed? So generally dynamic logic style will have faster working, that is speed will be there as seen in the last slide. So based on this capacitance and all the if you only this capacitance is the reason. If you use a reduced load, okay, reduced load capacitance, then your switching time and that is the charging and discharging time will be minimum. So charging and discharging time, if it is minimum, switching on and switching off, that is transition from one state to other state, will be faster. Okay, so this transition time, once it gets faster, automatically the speed, overall speed is determined as high. So we will be seeing the working of this dynamic CMOS logic. You have two phases, pre-charge and evaluation. In pre-charge phase, your MP will get pre-charged to higher voltage, that is VDD. Okay, so when clock is equal to 0, obviously when 0 is given to PMOS, PMOS turns on. So here I have VDD. So my VDD will move through this transistor and it will charge this capacitance. So if it is 5 volt, the 5 volt will be charged in CL. So this is an on condition. If my clock is 0, the same clock is given here. So what will happen? This clock makes the NMOS off. Okay, so this will be in off condition. Okay, so now you can understand there is no path from VDD to ground. Okay, so you will have the evaluation cuts also eliminate any static power during the pre-charge period. The reason is even if you during the evaluation phase only you will be giving the forcing the inputs here. Even after that, if you see, if this is on, you cannot have any path from VDD to ground. This is your evaluation phase. So when clock is equal to 1, this pre-charge transistor will be in off condition, and evaluation transistor, this one will be in on condition. So whenever you give a high voltage or 1, then your NMOS will turn on. Okay. So now you can see, depending upon this PDN, if you force the inputs now, if you give the inputs to pull down network, depending upon the transistor's status available, your capacitance will either get discharged to ground or it will stay the same. Okay, suppose I have one transistor here, or two, as shown in the diagram, I have three transistors. Three NMOS transistors, if they are fed with one, what happens? All the transistors will be in on condition. And as you know, during evaluation phase, this transistor is in on condition. So what happens? So you have moving off this CL already charged with VDD, moving from this point to ground. Okay, so if the inputs are such that the PDN conducts, okay, so depending upon the inputs given and depending upon the state of this transistor, either it will be on or in off condition. Okay, so if it is in off condition, the output will choose the low resistance path, that is it will move via this pull down network through this ME and go to ground. Okay, if PDN is not there, if it is turned off, what happens? Here the VDD is equal to 5 volt, just stored in the CL remains the same. Okay, and I told you earlier, CL is the combination of junction capacitance, wiring, and the input capacitance of fan out gates. So fan out gates, so here this will be given to drive some other circuit. No? So all these are fan out gates. So that will have some capacitance. So that will also come into account for the CL. And each and every transistor will have some capacitance, junction capacitance, so on. And the wires used here will have some capacitance. All these capacitance will be calculated together as CL. And now the inputs to the gate can therefore make only one transition during evaluation. Okay, during evaluation phase, whenever you force the input, okay, so only at a time, that is after pre-charge, depending upon this evaluation phase, the inputs fed into the PDN during evaluation phase, only one transition is possible, either 1 to 0 or 0 to 1 only is possible. And now you can see an example where an AND logic is designed using dynamic CMOS. Okay, just a pull down network consisting of two NMOS in series. So you have some important drawbacks or issues in dynamic CMOS logic: charge leakage, charge sharing, and capacitance coupling. Okay. So first we'll see what is charge leakage. So as you see, you have unnecessary parasitic diodes that is formed in your circuit. So I told you, whenever pre-charge happens via VDD, via MP, pre-charge transistor, you have VDD flow via MP and getting charged into your CL. So இங்க 5 volt இருக்குன்னா இந்த capacitance வந்து 5 volt சார்ஜா இருக்கும். இப்போ இந்த இடத்துல வந்து unnecessary diodes, reverse bias diodes, இல்லைன்னா வேற ஏதாவது parasitic circuits இருந்ததுன்னா they will consume some power. Okay, they will consume some power, and they will, because of these kind of circuits available over here, unnecessary circuits being formed over here, your charge will get leaked via those diodes, reverse bias diodes. இங்க இருக்கிற 5 voltல a part of this 5 volt will leak across this reverse bias diodes. Okay, so now you can see the diagram in pre-charge and evaluation phase. You can see that it is not complete. Okay, so your actual operation of this dynamic logic is totally dependent upon your CL. charging and discharging of CL. If 5 volt is not uh, exactly stored in CL, when you have uh, pull down network activated during evaluation phase, proper output will not move towards the next stage. So suppose I have an inverter over here. Okay, so here my input has to be 5 volt. Okay, for example, if my input has to be 5 volt, if this 5 volt is getting reduced to 3 volt because of this parasitics, what happens? My following fan out will not turn on. Okay, so this is the one of the main drawback, that is charge leakage. And next is your charge sharing. Okay, so this is more interesting. You can see when your clock is 0, your pre-charge transistor will allow the VDD to get charged into the CL. So இது வந்து 0 கொடுத்தோம்னா இது ஆன்ல இருக்கும். இது அந்த transistor வழியா VDD will move towards CL and it will get charged. So now CL is equal to, that is 5 volt will be stored inside CL. Now I am going into evaluation phase. Evaluation phase la clock வந்து 1. அப்போ this transistor will be in off condition. Whereas, so now you consider evaluation phase, this will be in off condition, so this is in on condition. Okay, and evaluation phase I have to give the inputs, I have to feed the inputs. So now if I feed the inputs, let me say I have A is equal to 1, that is 0 to 1 transition, and B is equal to 0. My NMOS will turn on for a 1, my NMOS will remain off for a 0. Okay, but my ME transistor is in on condition. So now what will happen? You have a low resistance path. Okay, so this will try to come till this point. Okay, so till this point it will try to come. The 5 volt available in this load capacitance will move from this output node. It will come to MA because this is a closed switch node. You have one. Okay, so it will come here. It will try to move from this point to via B transistor, but it cannot move because this is in off condition. Okay, so now what will happen? Now suppose you have 5 volt over here. Let me say 2 volt has come across this and it is getting stored in CA. Now charge is being shared between CL and CA. Okay, your entire 5 volt cannot move and reach to CA. The capacitance will be minimum. Okay, compared to this capacitance is a combined capacitance of all wiring, junction, and so on. Okay, so this transistor will have some diffusion capacitance, that is CA. இந்த டிரான்சிஸ்டர் MA அப்படிங்கிற டிரான்சிஸ்டருக்கு ஒரு கொஞ்சம் ஜங்ஷன் கெப்பாசிட்டன்ஸ், அதோட டெஃபியூஷன் கெப்பாசிட்டன்ஸ்லாம் இருக்கும். ஸோ அதுதான் CA. ஓகே, அப்போ இந்த இந்த கெப்பாசிட்டன்ஸ் எவ்வளோ வோல்டேஜ் எடுக்க முடியுமோ அதை எடுத்துரும். ஓகே, ஸோ திஸ் கால்ட் as charge sharing. The charge is shared between the capacitances. So whenever this kind of status occurs, where you have one NMOS is on and one NMOS is off, இதே இந்த இடத்துல 0 இந்த இடத்துல 1னா இந்த ப்ராப்ளம் வராது. Okay, the reason is you don't have low resistance path from output node. But when there is a path from output node to the next node, then there will be charge sharing. Okay, again, if this charge is getting reduced, what happens? Proper output will not be obtained for the next evaluation phase. Point number 1. Point number 2, this will not be able to drive the next gate. Okay. Next drawback is backgate coupling or capacitive coupling. So here you now you can see this diagram. This is my dynamic logic design, and imagine it is cascaded with a static logic. So this is a static logic. Okay, so now let me assume that this is the input. First it is 0. Okay, 0 first and then 1. Okay. So this is my normal dynamic logic style. So pre-charge transistor, evaluation transistor, and the inputs during the evaluation phase has to be 0 and 0 for M1 and M2. So now let's come with the flow. First, pre-charge phase. So pre-charge phase la clock வந்து 0, CMOS on la இருக்கும். So your VDD will be charged across this CL1. Okay, and after pre-charge phase, evaluation phase. Evaluation phase la clock வந்து 1. So இந்த இடத்துல உங்களுக்கு input speed பண்ணுவீங்க, and your clock 1 makes ME transistor on. So இது onல இருக்கும் evaluation phase la. இது வந்து offல இருக்கும். Now my inputs are applied. A is equal to 0, B is equal to 0. So what is my output now? output will have no change. Already available VDD will be there. Okay, already available VDD will be there in the CL1. Now, this already available VDD will tend to decrease because of this backgate coupling. You can see this. This is normal static logic. Okay. Now, we are assuming that first it is in 0. This in is 0. So first 0 இருந்துச்சுன்னா PMOS வந்து ஆன்ல இருக்கும், அவுட் 2 வந்து ஹைல இருக்கும். இப்போ evaluation phase-ல you are having a transition of this in from 0 to 1. Okay, இங்க வந்து pre-charge phase அப்போ இந்த இடத்துல வந்து 0 1 இருந்தா பிரச்சனை கிடையாது. Now I have an evaluation phase over here. Okay, during the evaluation phase இந்த இடத்துல வந்து ஒரு transition நடக்குது, 0 ல இருந்து 1 ஆகுது. அப்போ என்ன ஆகும் அப்படின்னா, if it is 1, PMOS has to be in off condition and out 2 has to be low, because PMOS off அப்படின்னா இந்த இடத்துல NMOS தான் ஆன்ல இருக்கும். All the voltages will be draining to ground via M4 and M3. Okay, but here out 2 will be pulled towards low. Meanwhile, out 1 also will be pulled to low. The reason is because of the coupling between out 1 and out 2. So back gate coupling between out 1 and out 2 is making my out 1 to go low. Okay, from 5 volt to some minimum value because of this coupling between out 2 and out 1. So this is one of the major drawbacks. So we have seen some of the issues. Let us see the advantages first. The number of transistors are reduced. It's ratioless, and static power consumption is minimum, and speed is higher. Okay. But what is the disadvantage? Clock requirement. Clock requirement means you need to generate clock. Okay. And what is one more disadvantage? You have some excess power consumption. In which case? During the recharge. Because you are forcing input during every evaluation phase. ஸோ எப்போவுமே வந்து ப்ரீசார்ஜ் எவாலுவேஷன் இப்படி தான் கிராஃப் போயிட்டே இருக்கும். ஸோ நீங்கள் வந்து ஃபஸ்ட்டு ஒரு இன்புட் வந்து ஃபோர்ஸ் பண்ணுறதுக்கு முன்னாடி ப்ரீசார்ஜ் பண்ணணும். அப்போ ஒவ்வொரு தடவை ப்ரீசார்ஜ் பண்ணிவிட்டு அதுக்கப்புறம் எவாலுவேட் பண்ணுறீங்க, ப்ரீசார்ஜ் பண்ணுறீங்க, மறுபடியும் எவாலுவேட் பண்ணுறீங்க. ஸோ எவ்ரி டைம் யூ ப்ரீசார்ஜ் there is some power consumption happening. Okay, so the disadvantage is because during evaluation phase only one transition can happen. Okay, so this is one of the drawback. And as you've seen in the video, that is the logic drawbacks, that is charge sharing, charge leakage, okay, capacitive coupling. So these are normal disadvantage or drawback, and we have some other methods to overcome this also. So that's all about your dynamic logic. So in the beginning of the slide, you have seen why should you prefer dynamic logic. So now you have why not dynamic logic. Okay, so they cannot operate at low speed, okay, which is one more drawback. When you go for complex circuits, this will be a major drawback. Okay, you want low speed in certain at certain applications. Okay, and they require a clock generation is a major problem. Charge sharing is the very big problem which is to be sorted out. Okay, and circuits are more sensitive to timing errors and noise, because if there is a time lapse between when you cascade dynamic logic, when there is a very small time lapse between the output changing from 0 to 1, okay, then all the rest of the operation will be collapsed. Fine. And the design is little more complex. Why more complex? When you go for bigger circuits, when you see the very basic circuit design seems to be simple, but when you go for very high-end circuits, sequential circuits, you will have many timings to be taken care. Okay, if a single timing, if it is missing, ஒரு சின்ன nanosecond change இருந்தாலும் இப்போ அவுட்புட் வந்து இப்போ உங்களுக்கு 0 to 1 transition நடக்கணும். அந்த 0 to 1 transition பொறுத்து தான் அடுத்த சர்க்கியூட் வந்து ஆன் ஆகிறதும் ஆஃப் ஆகிறதும் டிசைட் பண்ண முடியும். So even a very small change in design will collapse the entire working of the bigger circuit. So the design has to be more careful. Okay, so when we go for complex circuits, it's more difficult. So that's all about your dynamic logic. Greetings from the Department of ECE. In this video, Now we'll be learning about dynamic CMOS logic and NORA logic. So far we have seen many logic styles. First we saw what is CMOS static, both ratio and ratio-less, and we saw some of the switch logic design styles, transmission gate and pass transistor, and we have seen what is dynamic CMOS. So under dynamic circuit logic styles, you have dynamic, basic dynamic, that is pre-charge evaluation, basic block, and domino, NORA, DCVS, TSPC, all comes under dynamic circuit design. Okay. So this is your domino CMOS logic. Okay, so it is very simple, exactly similar to your dynamic CMOS logic style. In addition, you add a static inverter at the output. Okay, so in order to overcome the disadvantage that is present in the dynamic CMOS, you go for domino. So what is the disadvantage in case of dynamic CMOS? For a dynamic CMOS எடுத்துட்டீங்க அப்படின்னா, you will have uh, missing of that is you will have false input being fed to the fan out gates. That is, if you look at the actual working of dynamic CMOS, pre-charge evaluation அப்படி போயிட்டே இருக்கும். உங்களுக்கு வந்து ஒரு எவாலுவேஷன்ல ஒரு செட் ஆஃப் இன்புட்ஸ் ஃபோர்ஸ் பண்ணி யூ வில் பி கெட்டிங் த அவுட்புட். அடுத்த செட் ஆஃப் இன்புட்ஸ் ஃபோர்ஸ் பண்றதுக்கு முன்னாடி யூ ஹேவ் டு ப்ரீசார்ஜ் இட். Okay, so your sequence of working will go like pre-charge evaluation. Okay, so you will have a time lapse missing of some time period when you go for cascading of dynamic logic. So when you cascade 2 to 3 dynamic stages, you will not get the input, okay, being fed to the fan out gates. Suppose I have 2 stage or 3 stage, first stage உடைய output தான் அடுத்த second stage க்கு input ஆ போகணும், second stage உடைய output தான் third stage க்கு input ஆ போகணும். So இது எல்லாமே நீங்க டிசைன் பண்ற டைம்ல input ஆ உள்ள போகாது. Yeah, so there may be some delay. Okay, so due to various issues in dynamic CMOS, so என்ன ஆகும் அப்படின்னா, இந்த கேப்ல அந்த அவுட்புட் நோட்ல பிரசன்ட் ஆயிருக்கிற வோல்டேஜ் maybe a week 0 or week 1 will tend to act as the input for the next stage. So false input may be penetrating into the subsequent stages in case of dynamic CMOS logic. So false input வந்து உங்களுக்கு வந்து அடுத்த ஸ்டேஜுக்கு போறதுக்கு நிறைய சான்ஸ் இருக்கு dynamic CMOSல. This will be overcome in case of domino CMOS. Domino CMOS is also having some issues which you will see in the upcoming slides. Okay. So in this we have a plus point, that is you have attached an inverter. Okay, so when you see an inverter, you must understand that domino CMOS logic is aiming at only true logic design. Complementary output கிடையாது, true logic வந்து உங்களுக்கு வந்து கிடைக்கும், non inverting logic. Okay, the static inverter வந்து it acts as a buffer. Okay, and as usual you have, when clock is equal to 0, your pre-charged transistor, this makes the path available from VDD to the output node. Okay, pre-charge happens, the output node la உங்களுக்கு charge ஆகிறதா pre-charge. So இங்கே pre-charge நடக்கும். 5 வந்து 1 இருந்தது அப்படின்னா இந்த evaluation transistor on ஆயிரும், and depending upon the inputs fed to the NMOS logic or pull down network, you have the transition, that is இங்க எல்லாமே drain ஆயிருச்சு அப்படின்னா இந்த இடத்துல வந்து 0 இருக்கும், drain ஆகல அப்படின்னா the same VDD remains here. Okay, so pre-charge phase la you will have the charging up to VDD, and the since the output of since the output is VDD, the output of inverter will be 0 again. இதே evaluation phase la என்ன ஆகும், evaluation phase la ME transistor, evaluation transistor on ல இருக்கும். உங்களோட pull down networkல suppose if all the NMOS is on, okay, then the VDD will be pulled down to 0. Then what will be the output of inverter? 1. Okay, so that is why it is given as it makes a conditional transition from 0 to 1. If the inputs of pull down network are not 1, எல்லா NMOSும் ஆனா இல்ல அப்படின்னா உங்களுக்கு வந்து 0 to 1 transition நடக்காது. Okay, so one thing is made sure here. So என்ன அப்படின்னா, so all the inputs to the domino gates are set at 0 at the end of pre-charge period. How? Pre-charge la என்ன ஆகுது, you will have charging of the output node to VDD. Okay, so here the output of domino அப்படின்றது after inverter. Okay, so when your output node of the dynamic logic is VDD, உங்க இன்வெர்டர் சேர்த்தா தான் டாமினோ லாஜிக். அப்போ ஆக்சுவலா உங்களோட டாமினோ கேட்டோட அவுட்புட் வந்து ப்ரீசார்ஜ் முடிஞ்சதுக்கு அப்புறம் எப்பவுமே ஜீரோல இருக்கும். ஓகே, ஸோ அப்போ எவாலுவேஷன் ஃபேஸ்ல the transition that is possible, okay, is only either it can remain at zero or it can go from it can go for a 0 to 1 transition. Okay, so that is why the only possible transition is 0 to 1 transition. Okay, and இந்த இன்வெர்டர் இன்ட்ரடியூஸ் பண்றதுனால ரெண்டு உங்களுக்கு அட்வான்டேஜ் இருக்கு. ஃபர்ஸ்ட் வந்து it will be more immune to noise, and second வந்து கெப்பாசிட்டன்ஸ். ஸோ கெப்பாசிட்டன்ஸ் எப்படி அப்படின்னா the output node, ஸோ டைனமிக் அப்படின்னு வந்துட்டாலே உங்களோட கெப்பாசிட்டன்ஸ் சார்ஜிங் அண்ட் டிஸ்சார்ஜிங்கை பொறுத்து தான் the output will be evaluated. Okay, so actual dynamic logicல உங்களுக்கு வந்து CL load capacitance. Okay, CL load capacitance is a combination of all the sum of all the wiring capacitance, junction capacitance, இது எல்லாமே it will come into picture. Okay, but in case of static inverter, so this will have different capacitance. Okay, so compared to the entire dynamic logic, the pull down network, இது எல்லாத்தோடைய capacitance விட ஒரு normal inverter capacitance கம்மியா தான் இருக்கும். Okay, so it reduces the capacitance of the dynamic output node by separating your internal and load capacitances. Fine, so this will be more simpler, or it will be more lesser compared to the actual capacitance calculated in case of dynamic CMOS logic style. So this is your domino logic when you have two stages being cascaded. So let us just analyze how it is working. We have two phases, pre-charge and evaluation. Pre-charge la output node வந்து it will be charging to VDD. Evaluation la you will have forcing of inputs to the pull down network, and ME transistor, evaluation transistor will be in on condition. First pre-charge வந்து your clock will be 0. Okay, and your output obviously will be 1, charge to VDD. Okay, and output of inverter will be 0. Again, in case of second stage, clock 0, output 1, output of inverter is 0. Now come to evaluation phase. Evaluation phase la clock is equal to 1. Clock வந்து 1 அப்படின்னா PMOS வந்து off ஆயிரும். Pre-charge transistor will be in off condition and evaluation transistor will be in on condition. Okay, இப்போ எல்லா இன்புட்ஸும் 1, எல்லா இன்புட்ஸும் 0. சிம்பிளா we'll analyze and see what happens when all inputs are 1, what happens when all inputs are 0. Okay, so, when all inputs are 1 to pull down network, that means your entire you have a path from this node, output node, to ground. Ingi NMOS will act as a closed switch. If all the inputs are 1, then all these NMOS will be on. So there is a direct path from this output node to ground. Okay, so it is going to 0. And if it is going to 0, output of inverter will be 1. Now again in this case all inputs are 1. What happens? Again the output of second stage also will be drained to ground. Output of inverter will be 1. So this is how it operates. All inputs are 0 அப்படின்னா the same VDD is retains at the output node, first stage and second stage as well. Okay, so in this you must understand that the pre-charge will happen in parallel. Okay, pre-charging will happen in parallel when you cascade domino logic. Okay, I told you dynamic logic la இருக்கிற disadvantage domino வந்து overcome பண்ணும். Dynamic la உங்களுக்கு எப்படி pre-charge evaluation step by step வருதோ இங்க அப்படி இருக்காது. Pre-charge will happen parallelly for all the cascaded stages, and evaluation will happen in sequential, step by step. First stage first evaluation நடக்கும், அடுத்து second stage, அடுத்து third stage, it will go on in steps. So parallel pre-charge and sequential evaluation. So that is why we are able to overcome the disadvantage in case of dynamic logic. So this is an example which I have stated. So you have included one more domino CMOS logic involving two stages cascaded with each other. As seen in the last slide, you can see how pre-charge happens parallelly and how evaluation happens sequentially. So this is how evaluation happens sequentially. So first evaluation phase and second evaluation phase, third evaluation phase. So this is how it happens. So one thing you must understand here, there is a problem that is happening in domino CMOS which is called as ripple pre-charge. you can note that there is a time lapse between each and every evaluate phase. ஒரு evaluate phase க்கும் இன்னொரு evaluate phase க்கும் ஒரு minimal time gap இருக்கு. Okay, so you have mild time gap. So okay, so there is mild gap between one evaluate and another evaluate. So let me say it clearly. So you have the first stage. Okay, you want to feed this input to the next stage. Likewise, if you have 3 or 4 stages, what will happen? Now you are pre-charging this and then you are evaluating this. Okay, when you evaluate this, you have to wait until this inverter, until this output passes through the inverter, and then it will go to the next domino stage. Okay, so that there is a delay happening over here. So you might wonder, this is not a a great delay, this is not a big delay, but that mild value, a very small delay, will propagate through the stages, okay, as ripple precharge. So it will move towards in subsequent stages. You can see the effect of the ripple that is happening in the first stage. Okay, so the input to the second gate is initially high and it will take 2 gate delay. 2 gate delay is nothing but you know the this gate and this gate. Okay, before x is driven low. So before this is made low, here I have, after precharge I have VDD. So this VDD is being made low here. Okay, so எப்போ low ஆகும், இந்த evaluation phase முடிக்கணும், அப்புறம் இது வழியா W வந்து it has to pass through this inverter. So 2 gate delay it has to wait. So first stageல 2 gate delay னா அப்புறம் அடுத்த stageல அதுக்கு ஏத்த மாதிரி delay வந்து increase ஆயிட்டே போயிட்டே இருக்கும். Okay, so third gate will have to wait until the second gate precharges, and then the fourth gate, and so on. Okay, so this time taken to precharge and evaluate, or time taken to precharge logic circuit. Okay, so this delay will come into the critical path. Okay, the time taken to obtain the output, the critical path will be will become lengthier more. So we have few advantages and disadvantages. Advantages: high speed and less number of transistors. So high speed can be justified using minimum capacitance. So why minimum capacitance is stated? You can that means why minimum capacitance is possible. Minimum capacitance is possible with the help of buffer or inverter at the output of your static inverter at the output of your domino. So that reduces the actual capacitance at the output node. If when you take dynamic case, you at the output you have CL, that is load capacitance, which accounts for all wiring, junction capacitance, and so on. But in case of inverter, compared to the actual dynamic capacitance, the inverter output node capacitance is minimum. So when the capacitance is minimum, charging and discharging time is minimum, so you have more speed, and the number of transistors is required is just n plus 4, and that is a pre-charge transistor, evaluation transistor, and 2 transistors for static inverter. Okay, so n plus 4. The number of inverting that is inverters that is connected at the output has to be even. If you have cascaded many domino stages, the number of inverters has to be even number, so that 0 to 1 transitions is possible. Okay, and you cannot implement complementary logic, you can implement only true logic here. Okay, and since again compared to dynamic and dynamic, here also you have pre-charge and evaluation. So wherever there is pre-charge, you will have charge leakage and charge sharing, both the problems will be there. So this is your NP CMOS logic. So you can see that you have 2 stages being cascaded. Actually, it is a series of cascaded stages in which you have pull down network followed by pull up network. அதாவது first stage வந்து similar to what you have seen in dynamic and domino. You have a pre-charge transistor, you have an evaluation transistor. Both are driven with the same clock, and you have inputs being fed to the pull down network, that is using NMOS transistors. The logic is being designed in the NMOS network. Okay, followed by you have a um, evaluation transistor as PMOS, and pull up network. Using pull up network, you will be designing the logic. Okay, and pre-charge transistor will be your PMOS, where this stage is being driven by clock and this stage is being controlled by clock bar. Okay, so again to PDN and followed by to PUN. So like this, you will be alternating this PDN and PUN, pull down network and pull up network. Okay, so this two stages will repeat forever. Okay, for designing your logic. So you have normal, pre-charge and evaluation transistor as your PMOS and NMOS, and your pull-down network designs the logic. Okay, the output of this stage will be given to the pull-up network. Okay, and here I have PMOS as evaluation transistor and NMOS as pre-charge transistor, in which you control it using clock bar. Okay, so now what happens when clock is equal to 0? This stage it is getting pre-charged. Okay, and when clock is equal to 0, this transistor is in off condition. Here when clock is equal to 0, this is 1, so this is in off condition. Okay, and here this pre-charge, here also pre-charge happens. So here pre-charge happens and here pre-charge happens. So இங்க pre-charge ன்னு சொல்ல முடியாது, அதுக்கு பதிலா நம்ம என்ன சொல்றோம், pre-discharge ன்னு சொல்றோம். இப்போ clock is equal to 0 அப்படின்னா clock bar 1. ஸோ இந்த டிரான்சிஸ்டர் ஆன்ல இருக்கு, இந்த டிரான்சிஸ்டர் ஆன்ல இருக்கும். இது வந்து ஆன்ல இருக்கும்போது என்ன ஆகும், இந்த நோட்ல இருக்கிற எல்லா வோல்டேஜும் it will drain off to the ground. Okay, so this is called as pre-discharging to 0, and this is called as pre-charging, this is called as pre-discharging. Okay, and in the evaluation phase you have again clock is equal to 1. Okay, so clock is equal to 1 அப்படின்னா இந்த இடத்துல உங்களுக்கு வந்து transistor will be in closed switch. Here the inputs will be applied and automatically the output of this will be given as an input to the pull-up network. Okay, when clock is equal to 1, clock bar is equal to 0. So this transistor will be in on condition. So இந்த block வந்து onல இருக்கும், VDD ல இருந்து path இருக்கும். Okay, so depending upon the inputs given to PUN, there will be a path from VDD to the out to. Okay, so you have both transitions being possible, 0 to 1 and 1 to 0. So 0 to 1 transitions in case of PDN, as we have seen in dynamic and domino, after pre-charge and every evaluation phase, 0 to 1 is made possible. Here, when in case of PUN, that is pull-up network, you will have transition 1 to 0 possible after the end of evaluation. Okay, so in terms of P tree and N tree, we'll be discussing it. Okay, so P tree அப்படின்னா full up network யூஸ் பண்ணிருப்பாங்கல்ல அந்த ஸ்டேஜ்க்கு வந்து P tree. N tree அப்படின்னா full down network யூஸ் பண்ணி logic design பண்ணிருக்காங்கல்ல அது N tree. Okay, so P tree is controlled by your clock and N tree is controlled by clock bar or vice versa. Okay, and your NP-CMOS is actually using the principle of duality, that is between your pull-up network and pull-down network, to eliminate race condition. Race condition சொல்லலாம், அப்படி இல்லைன்னா the ripple that is propagating through the stages, which will make the critical path become more complex. What we have seen in case of dynamic logic style, okay, and domino logic style. Dominoல race condition இல்லைன்னா critical path increase ஆகுறதுன்னு சொல்லலாம். டைனமிக்கை பொறுத்த வரைக்கும் ஃபால்ஸ் இன்புட் அடுத்த ஸ்டேஜுக்கு போகிறது. இது ரெண்டையும் ஓவர் கம் பண்ணுறதுக்கு தான் இந்த NP-CMOS லாஜிக். ஓகேயா, ஸோ ஆஸ் யூ ஹவ் சீன் வாட் ஹேப்பன்ஸ் இன் ப்ரீசார்ஜ் ஃபேஸ். ப்ரீசார்ஜ் ஃபேஸில் உங்களுடைய ஃபர்ஸ்ட் ஸ்டேஜ் புல் டவுன் நெட்வொர்க் யூஸ் பண்ணியிருந்தீங்கல்ல, அந்த ஸ்டேஜில் ப்ரீசார்ஜ் டிரான்சிஸ்டர் வில் ப்ரீசார்ஜ் டு VDD. செகண்ட் ஸ்டேஜில் புல் அப் நெட்வொர்க் யூஸ் பண்ணி டிசைன் பண்ணியிருக்கிற ஸ்டேஜில் NMOS transistor will be pre-discharged to 0. Okay, and during evaluation phase what happens, okay, the pull down networkல இருந்து வர்ற அவுட்புட்டை வந்து pull up networkக்கு நீங்க கொடுக்குறீங்க. Okay, so in case of first stage 0 to 1 is possible and 1 to 0 is possible in case of the output of second stage. அப்போ இதுல என்ன டிஸ்அட்வான்டேஜ் அப்படின்னா உங்களுக்கு ரெண்டு டிரான்சிஷன் ஈஸியா பாசிபிளா கிடைக்கும். பட் compared to when you design the logic using PMOS, okay, generally PMOS is less efficient when compared to NMOS. ஏன் அப்படின்னு பார்த்தீங்கன்னா NMOS கொடுக்குற மாதிரி அவுட்புட் ட்ரெயின் கரண்ட் வந்து PMOS வந்து கொடுக்காது. அதுக்கு ரீசன் ஜென்ரலாகவே மொபிலிட்டி வந்து P டைப் வந்து கம்மி. ஓகே, ஸோ யூ ஹாவ் லெஸ் மொபிலிட்டி in case of P type materials, and the reason you follow the sizing ratio is to compare the efficiency between NMOS and PMOS. ரெண்டும் ஒரே லெவல்ல பெர்ஃபார்ம் பண்ணுங்கிறதுக்காக தான் இந்த சைசிங் ரூல்ஸ் எல்லாம் போடுவாங்க. Okay, so இந்த sizing rules யூஸ் பண்ணி தான் உங்களால optimize பண்ண முடியும் performance. Okay, so that is why always you find PMOS to be of larger size. So you have two disadvantages over here. So P3 blocks are slower. Okay, and one more thing, so including this PMOS network, pull up network will increase area also. Okay, so this two reasons, two causes will act as the major disadvantage in case of NPCMOS. So this is NORA, so in which you have added an inverter at all the output stages. ஒவ்வொரு அவுட்புட் ஸ்டேஜ்லையும் உங்களுக்கு இன்வெர்டர் ஆட் பண்ணி நீங்கள் அடுத்த ஸ்டேஜுக்கு கொடுக்குற மாதிரி கொடுத்துருக்கீங்க. ஓகே, ஸோ ஒன்லி ஒன் டிஸ்அட்வான்டேஜ், திஸ் இஸ் வெரி சென்சிட்டிவ் டு நாய்ஸ். And when phi is equal to low, that is clock is low, the NMOS will be pre-charging to VDD and PMOS will be pre-discharging to 0 as seen in the last case. Okay, same is being followed. Inverter add பண்ணீங்கன்னா then you have this as NORA or no race condition logic. என்ன டிஸ்அட்வான்டேஜ், என்ன அட்வான்டேஜ்? அட்வான்டேஜ் வந்து ஒவ்வொரு இதுலேயுமே வந்து இன்வெர்டர் வந்து ஆட் பண்ணுங்கிற அவசியம் இல்லை. என்மாஸ் ஸ்டேஜில் மட்டும் ஆட் பண்ணால் இட் இஸ் enough. Okay, and you can have pipeline system architecture, but again wherever there is recharge, wherever there is evaluation, you have charge sharing and charge leakage. So this is the disadvantage. So that's all about your dynamic, the domino and NORA logic styles. Greetings from the Department of ECE. In this video, we'll be learning about TSPC dynamic logic. So far we have seen static, ratio-less, and then we move towards switch logic, transmission gate and pass transistor, and then we move towards dynamic logic styles. So basic dynamic logic style, recharge and evaluation phase, all those we have seen, and domino, which will include both the transitions being possible, and NORA, okay, no race condition, and then now we are into TSPC, that is two single. So why TSPC? So if you see a normal chip design, and if I'm designing a chip and I have allotted some power, uh, for example, ஒரு பர்டிகுலர் சிப்புக்கு இவ்வளோ பவர் நான் அலாட் பண்ணியிருக்கேன் அப்படின்னா, அந்த அலாட் பண்ண பவரில் ஓவரால் பவர் கன்சம்ஷன் பார்க்கும்போது அதில் 50% ஆஃப் த பவர் வில் பி கன்சியூம்ட் ஃபார் கிளாக் ஜென்ரேஷன் அண்ட் கிளாக் டிஸ்ட்ரிபியூஷன். இந்த கிளாக் டிஸ்ட்ரிபியூஷனுக்கு நிறைய பவர் வந்து கன்சியூம் ஆகும். த ரீசன் இஸ், for example, when you go for two-phase clock, okay, clock bar ரெண்டு விதமா நீங்க கொடுக்கணும். நான் ஓவர்லாப்பிங்காகவும் இருக்கணும். நான் ஓவர்லாப்பிங் அப்படின்னா clock பாரும் it will not overlap. When it is in 0, clock bar will be in 1. So non overlappingaகவும் இருக்கணும், and it should be properly disseminated, properly distributed to all the nodes at appropriate times. Okay, so that has to be taken care. And whenever you use more number of phase, the wires will increase, that is interconnections will go on increasing. So lengthy interconnects as well as more number of interconnects will result in RLC, parasitic RLC. Okay, and each and every wire have its own associated capacitance. They are conductors, they will have its own capacitance. Okay, so these all will change the working of my circuit. So எப்போல்லாம் RLC உங்களுக்கு கூடுதோ அப்போல்லாம் உங்களுக்கு performance வந்து உங்களுக்கு கம்மியாகும். Unnecessary RLC combinations வரப்போ obviously your performance will get degraded. Okay, and the main problem is clock skew. For example, dynamic logic style, we learned that when you cascade dynamic logic style, you face some problem. Transitionல கொஞ்சம் ப்ராப்ளம் இருக்குன்னு பார்த்தீங்க. இப்போ ஒரு 4 ஸ்டேஜ் இருக்குன்னா ஒவ்வொரு ஸ்டேஜுக்கும் நம்ம கிளாக் வந்து கொடுக்கணும். For all the stages, clock will not go at the same time. That is clock skew. And it will not be acting in the same way because clock is not distributed at the same time. For example, first stage 0 nanoseconds, second stage 4 nanoseconds, third stage 8 nanoseconds. It may differ. Okay, so this difference, they are because of thousands of reasons are there, but this difference will cause degradation in my working of the circuit. Okay, so இதெல்லாம் அவாய்ட் பண்றதுக்கு சிங்கிள் ஃபேஸ் கிளாக் வந்து நம்ம கொண்டு வரணும். ஒரே வேல்யூ கிளாக் மட்டும் யூஸ் பண்ணி உங்க சர்க்கியூட் வந்து ஒர்க் பண்ணணும். கிளாக் மட்டும் தான் இருக்கணும், கிளாக் பார் யூஸ் பண்ணக்கூடாது. Okay, so in the early 1970s and 1930s itself, the single phase clock design came into picture. Okay, these people, Ivan and Swenson, they tried designing a frequency divider circuit and a latch using this single phase clock system. Okay, so dynamic first we have seen, and then domino. So dynamic had some problem in offering both the transitions, and then we moved towards domino with the inverter at the output, buffer at the output, and then we had some race problem. So now we are moving towards NORA, okay, which will avoid the race conditions. Okay, so in the early 1970s itself, those two people which we have seen in the last slide, so they tried all these logic styles. Okay, so dynamic domino, um, some more logic styles are also there. C square MOS, that is clock to CMOS. So இதெல்லாம் நிறைய logic styles. They had their own advantages and disadvantages. So using all these they designed, and finally they came out with a single phase clocking to go for a latch design and uh, a frequency divider. Okay, so there it started. So first we learn how to um, design a single phase positive latch. Okay, so this concept TSPC we are learning to as a dynamic logic style to design dynamic circuits. Okay, the very basic dynamic circuit will start now. Latch. Okay, so first we'll design a positive latch using single phase clocking. This is a positive latch. Okay, where single phase clock only clock is used. Okay, so now latch now உங்களுக்கு transparent mode, hold mode ரெண்டு இருக்கும். Okay, latch it will conduct the value or it will retain the value. So conduct பண்ணுச்சுன்னா transparent mode, hold பண்ணுச்சு retain பண்ணுச்சுன்னா அது வந்து hold mode. Okay, so now transparent mode la, so my clock will be 1, and what happens when my input is 0 and 1, we will see that. Okay, so now clock is equal to 1, it is in transparent mode. Okay, clock is equal to 1 and input is 0. Input 0 now PMOS on condition, NMOS is in off condition. Okay, so PMOS on அப்படின்னா என்ன ஆகும், VDD ல இருந்து path இருக்கு output, so pre-charge ஆகும் and output will be high. Okay, so this high output will turn off my PMOS in the second inverter. Okay, and NMOS will be in on condition. So இப்போ ரெண்டு NMOSமே onல இருக்கு, this NMOS is in on and this NMOS is in on condition. So you'll have path from output to ground. Okay, so you have a 0. Is my latch conducting? So I have a 0 here, I have a 0 uptime here. So it is in transparent mode when the clock is 1. What happens when input is 1? Input 1 are the NMOS on off, PMOS off condition level. Okay, now if my PMOS is in off condition, obviously all the voltage at output will be drained to 0, and here my value 0 will be obtained. Again, this 0 will switch on a PMOS. This is in on condition, and PMOS NMOS off condition. Okay, so PMOS on la irundhudu appadina pre-charge agum, so you have a high output 1. Okay, now is my latch conducting 1? Yes, it is conducting. What happens when your when your clock is 0? Okay, clock 0 varudhuna, it will retain the same state. Okay, it will not conduct, but it will retain the same state based upon your input. Okay, so now we have learned what is positive latch. We'll go for negative latch also. Negative latch la உங்களுக்கு அப்படியே இது working வந்து similar தான், but what is different is here when clock is equal to 0, my latch will be in transparent mode, where when clock is equal to 1, it will act in the hold mode. That is 0 இருக்கும்போது it will conduct the value, inல இருந்து அவுட்டுக்கு வேல்யூ வந்து ஈஸியா ப்ரொபகேட் ஆகும். 1 இருக்கும்போது hold mode இருக்கும் அப்படின்னா உங்களோட வேல்யூ வந்து retain ஆகும். The state will be retained depending upon the input you feed. Okay, so now we have learned the very basic circuit latch, that is positive latch and negative latch. When you cascade both positive latch and negative latch, you obtain a register. Okay, latchuக்கும் ரெஜிஸ்டருக்கும் என்ன வித்தியாசம் அப்படின்னா, latchங்கிறது லெவல் ட்ரிகர். உங்களோட அவுட்புட் வந்து it comes into that is your output will be obtained when you maintain uh, the level 0 and 1. அது வந்து level triggered. Okay, edge triggered na your output will be obtained when you encounter a rising edge or a falling edge. Okay, rising edge na 0 to 1, falling edge na 1 to 0. So level triggered அப்படின்றது உங்களோட இன்புட் லெவலை பொறுத்து அவுட்புட் வந்து ரெஸ்பாண்ட் பண்ணும். எட்ஜ் ட்ரிகர்ட் அப்படின்றது இன்புட்டோட எட்ஜ் கண்டிஷன், அதாவது உங்களோட ரைசிங் எட்ஜில் இருக்கா இல்லை ஃபாலிங் எட்ஜ் இருக்கா, அந்த கண்டிஷன் அட் தட் இன்ஸ்டன்ட் ஆஃப் டைம் யுவர் அவுட்புட் வில் பி, you can see the response. Okay, so when you cascade both positive and negative latch, you obtain a register. In upcoming slides, you will see how to design a register, and you will see a D flip-flop, that is D register, in the last slide. Okay. So here the advantage is clock is being reduced. Clock load illa. Disadvantage enna அப்படின்னா number of transistors வந்து இன்னும் கொஞ்சம் ஜாஸ்தியா இருக்கு. Okay. So practically speaking, when you compare your static and dynamic latch, that is static and dynamic resistors, dynamic seems to have less number of transistors. Okay. In some cases, rare cases, you find number of transistors being increased. So this is the simplified version of true single phase clock latch. So you may wonder, why should I learn this simplified version? So simplified version ங்கிறது உங்களுக்கு வந்து வெறும் அந்த first inverter மட்டும் இருக்கும். Second வந்து you can implement based upon your design. Okay, you can implement either logic, or you can go for a simple inverter again, or using if you want to form a negative and positive latch. Okay, and clock is being reduced. You can see in the diagram, clock இதுல வந்து feed பண்ணல. Okay, yeah. So this is a simplified true single phase clock latch. Okay, so only first inverter is retained, which is controlled by your clock. Okay, so இதுல என்ன main advantage na transistors கம்மியாயிரும், clock-ம் கம்மியாயிருச்சு. Okay, so this is one of the main plus point. Okay, so but இதுல ஒரு problem இருக்கு. என்ன problem அப்படின்னா, you will have same charge sharing problem over here. என்ன மாதிரி அப்படின்னா, so suppose ரெண்டுமே positive and negative latch கொடுத்திருக்காங்க. ரெண்டுமே when it is in transparent mode, when your input is 0 in case of positive latch, what happens? PMOS onல இருக்கும், NMOS offல இருக்கும், clock வந்து 1 transparent mode தான். Okay, so இப்போ PMOS வந்து onல இருக்கு அப்படின்னா, it will conduct and it will provide VDD at the output. Okay, so now I have VDD at the output, but what is at node A? This node A is the driving point of next transistor. இந்த நோட்ல என்ன இருக்கு அப்படின்னு பார்த்தீங்கன்னா, VDD minus VTN தான் இருக்கு. Okay, so this transistor, okay, so it will not turn on the next NMOS. This nodal voltage, this will not turn on the next NMOS. Okay, this is a problem in case of positive latch. இதே negative latchல பார்த்தீங்கன்னா, so it requires a strong one to on. Okay, so that is not possible. So ரெண்டு ரீசன் சொல்லலாம். இந்த இடத்துல சார்ஜ் ஷேரிங் அதுவும் ஒரு ரீசன். இன்னொரு ரீசன் இந்த இடத்துல ஏன் VDD minus VTNனா, NMOS cannot pass a strong one. It can pass a strong 0, but cannot pass a strong 1. It cannot. Okay, so that is also two reasons are there: charge sharing as well as NMOS cannot pass a strong 1. And in case of negative latch, if you see, அதே மாதிரி transparent modeல negative latchல input வந்து ஹையா இருக்கும்போது PMOS off conditionல NMOS on conditionல இருக்கும், and clock is 0 obviously for a transparent mode of positive negative latch. Okay, so now what will be the condition? ரெண்டு NMOS on conditionல இருக்கு. The output will be drained to ground, that is you will have here it is supposed to be 0, but it is not 0. Okay, so PMOS cannot pass a strong 0, so here VTP will be there. This may not on the next transistor. Okay, so this is one of the disadvantage in case of your true single phase clock latch. Simplified version is a disadvantage. Okay, now this is a diagram of TSPC which shows that you can implement logic instead of that single PMOS and NMOS. So இந்த இடத்துல ஒரு single NMOS ஒரு single PMOS போட்டிங்கன்னா cascading of positive and negative latch னு சொல்லலாம். Okay, so இங்க வந்து you can implement logic also. Okay, so when similar working, when clock is low, your pre-charge happens. Okay, and this block will evaluate, this block will pre-charge. அதே மாதிரி இங்க clock வந்து ஹையா இருக்கும்போது இது வந்து pre-discharge ஆகும். Okay, and this blocks will evaluate. Okay, so here 5 only is used, 5 bar is not used. Okay, and these also provide pipeline applications, pipeline structure கொடுக்கும். So exactly similar to NORA it will operate. So I told you we will learn basic D flip-flop or D register. Okay, rising edge triggered D flip-flop. So D flip-flop na romba simple. Kudukura value அப்படியே வெளியில வரும். Okay, yeah? So rising edge triggered na your when it moves from 0 to 1, my output has to respond. Okay, so this is my D flip-flop using TSPC logic style. Now, when clock is equal to 0, positive latch is in transparent mode. Okay, and this will pre-charge now. Okay, and what about the last inverter? So, இது ரெண்டு தான் inverter. Okay, so in இப்போ clock 0 இருக்கிறப்போ D input உள்ள வரும். இது sample பண்ணி that is it will get the value of D. Okay, and this will pre-charge, and the final inverter will be in hold mode. Okay, when clock is equal when clock is moving from 0 to 1, rising edge triggered இல்லையா? So rising edgeல போறப்போ இது வந்து evaluation phaseல வந்துரும். The inputs will be evaluated and the final inverter will be in transparent mode. Okay, so when it is moving from 0 to 1, clock வந்து 0 to 1 move ஆகும்போது உங்களோட input value D will be obtained as Q here. So the detailed explanation I have given in the next slide in form of theory. You can go through. So here when I see I require only 11 transistors. 3, 3, 3, 9 transistors, 9 plus 2 for inverter. 11 transistors. So similarly when you design D flip-flop using static that is static latch use பண்ணி design பண்ணும்போது 16 transistors வேணும். But now I require only 11 transistors. So this is how it works. When clock is equal to 0, sampling your input will happen, and the second inverter will go to pre-charge mode. Final inverter will be in hold mode. இதே வந்து clock வந்து 1 இருக்கும்போது அதாவது rising edge 0 to 1க்கு போறப்போ உங்களோட first inverter வந்து evaluate பண்ணும், input evaluate பண்ணும், and final inverter will conduct the value. Okay, that is output Q will be generated. So in an advantage வந்து you can have you can design both latch as well as logic. So latch, register இதெல்லாம் design பண்ணலாம். Apart from that you can embed logic into the TSPC pipeline structure. As you have seen before the D flip-flop, I showed you CMOS logic and PMOS logic. So where you can embed your logic. Okay, logic design பண்ணலாம். Now all the common advantages that is applicable for basic dynamic logic cell will be applicable here also. And when you design properly, when you design with more clarity, you can have a glitch-free system in case of TSPC. And very importantly, no clock skew problem is available. Okay, the only disadvantage that you can tell is in at certain cases you will have more number of transistors, and when you go for a simplified TSPC, the strong 1, strong 0 problems is revisiting here. Okay, so that's all about your TSPC logic design style. Greetings from the Department of ECE. In this video, we'll be learning about differential cascade voltage switch project. So we are in the last logic style, that is DCVS, which is a very simple logic style. So this is the block diagram using which differential cascade voltage switch logic is designed. So the name has come from the property that it uses the differential property. That is, you will use two networks to obtain true as well as complementary output. Okay, so you will use both the set of inputs, true inputs and complementary inputs, and output also will be obtained as true as well as complementary. And the load will be used as a single PMOS for both the pull-down networks. Okay, you have cross-coupled PMOS transistors with positive feedback. Okay, so this will act as a overall load for entire logic. So the main property or the main feature over here is you can generate both true as well as complementary output at the same time. Okay, that is why it is called as differential. And the load is also properly designed using two PMOS transistors. You can see they are cross coupled. That is, ஒரு PMOS உடைய output வந்து sorry one இது ஒரு for example M1 உடைய input வந்து out bar கூட, அதே மாதிரி M2 உடைய input வந்து out கூட. They are cross coupled with outputs. Okay, so and as usual at any instant, okay, any one pull down network only will be in on condition, okay, or will be active, and no static power. So you don't have path from VDD to ground. Supply and the ground, there is no path. Only at that instant you can get no static power consumption. And this is a ratio logic. That is, you have to maintain a ratio, W by L ratio between pull up and pull down network. So now we will check how to design AND as well as NAND logic using DC VSL logic style. So this is the circuit diagram. Just like how we have seen in the block diagram, we have two blocks, that is A and B, pull down network, that is using the true inputs. One more PDN block, that is using your complementary inputs. A bar B bar use பண்ணி ஒரு PDN block இருக்கும், A B use பண்ணி ஒரு PDN block இருக்கும். And your PMOS is connected cross coupled to the output nodes. Okay, and one thing you must note before going into checking each and every combination is out is considered as NAND over here, out bar is considered as AND logic. Just like normal CMOS logic style, right from CMOS static, whenever you try to implement any A dot B, you get a B bar, okay, in every CMOS style. Okay, so here it is AB bar and here it is AB. So in case of table, I have given out bar as and out as NAND. Okay, so now we will check how it proceeds for each and every combination. First, A is equal to 0, B is equal to 0. Okay, so these both values will make M1 and M2 off, A bar 1 and B bar 1. So these two values will make my my transistors M3 and M4 on. Okay, so அப்போ இந்த நோட்ல இருக்கிற எல்லா வோல்டேஜும் it will try to come down. That is, at this node, even if there is some minimum voltage, it will pass to ground. Now at this node you have a 0. You can see from this node it is being connected to your this PMOS. Okay, so this PMOS will turn on for a 0. Okay, so if this turns on, what happens? Right from VDD you have a path. Okay, so it recharges. Okay, so it charges, so you get a 1 over here. Okay, you get a 1 over here, and at this output, so இங்க 1 அப்படின்னா இந்த நோட்ல உங்களுக்கு என்ன nodal voltage 1. So இந்த 1 என்ன பண்ணும்னா, this will in turn go as a input to this PMOS. Okay, so this PMOS cannot turn on because 1 is being fed as an input. So this will remain in off condition and your output will be 0. Okay, so this is how you obtain a 0 and 1. And if you see the next one, A is still a 0 and B is 1. So now B, suppose if you have 1, B bar will be 0. Again, what will be the condition? So if only if one transistor is on in this case, you will have draining to 0. Okay, so ஏதாவது ஒரு transistor on இருந்தாலும் ரெண்டு transistor on இருந்தாலும் இங்க என்ன voltage இருந்தாலும் that will go down to ground. Okay, so இங்க now you have one A bar, that is this is still on. Okay, so it will go to ground and still a voltage 0 is maintained. Same condition, இங்க 0 அப்படின்னா இந்த transistor on ஆகும், இங்க 1 இருக்கும். இங்க 1 அப்படின்னா இந்த transistor will be off condition and it will give a 0. Okay, so same voltage at output node will be retained and hence the same output will be obtained. Next வந்து உங்களுக்கு வந்து A1 B0. Okay, so இப்போ A1 அப்படின்னா A bar will be 0. Okay, and now also you can see here A is equal to 1, B is equal to 0, this will be off condition, and A bar is equal to 0, again off condition, B is equal to 0, B bar is equal to 1. So this M4 will be non condition. So you have M1 and M4 in off and M2 and M3 in on. அப்போ ஏதோ ஒரு டிரான்சிஸ்டர் இந்த parallel blockல ஏதோ ஒரு டிரான்சிஸ்டர் ஆன்ல இருக்கு, ஒன்னு ஆன்ல இருந்தாலும் ரெண்டுமே ஆன்ல இருந்தாலும் இங்க இருக்கிற எல்லா வோல்டேஜும் கிரவுண்டுக்கு போயிடும். again a 0 is maintained here. இங்க 0 அப்படின்னா இந்த 0 தான் இந்த பாத் வழியே இந்த PMOS ஆன் பண்ணுது. So this will have a 1. Okay, it will give a 1 since it is getting charged through VDD, and this 1 will act as an input to this PMOS. So this PMOS will still remain in off condition and output will be maintained as 0. Okay, so now at last you have both the transistors fed as 1. Okay, now you have here it is A B ரெண்டுமே 1 அப்படின்னா A bar B bar ரெண்டுமே 0. ஓகே, ஸோ அப்போ இங்கே ரெண்டுமே 0 அப்படின்னா உங்களுக்கு ஆஃப் கண்டிஷனில் இருக்கு. பட் லுக் அட் திஸ் ஸ்டேட். Okay, so already it was 1. Okay, already it was 1. Now if both the transistors are on, A1 B1 அப்படின்னா இந்த ரெண்டு டிரான்சிஸ்டர் ஆன்ல இருக்கும். இங்க இருக்கிற 1 வந்து it will be drained down to ground. Okay, so now you have a 0 here. Okay, now this 0 will go to this PMOS as an input and it will turn it on. Okay, இது on ஆச்சுன்னா it will charge via VDD and you get a 1 over here. And this 1, okay, it will act as this nodal voltage and this will in turn go as an input for this PMOS. So in the PMOS ku 1 போச்சுன்னா இது off ல இருக்கும். So it is 0. Okay, now we have a change. Fine, this is how a normal DC VSL works. So we have few advantages and disadvantages. So first and foremost advantage can be it can it can give both true and complementary output. Okay, even though it is giving true and complementary output, accordingly I have to include the number of transistors. As you can see, we had two blocks, PDN1 and PDN2. ரெண்டு pull down blocks introduce பண்ணோம். So you have more number of transistors. Okay, and no need of buffer or inverter. You have a very in established PMOS load. Okay, that will assist in giving a 0 as well as 1. Okay, and no static power consumption. Static power consumption illa reason you have no path, straight path from VDD to ground. At a time you have either the PMOS load or any one pull down network being active. And the design is complex. Yes, when you go for basic gates பார்க்கும்போது it seems very simple. Even when you analyze XOR and XNOR, it will be a bit more difficult. And when you go for Boolean logic, different Boolean logic to be established, again it becomes little more complex. You have to design in such a way. Okay, and dynamic power dissipation. So here you have dynamic power dissipation. So static power consumption இல்லாட்டியும் dynamic power dissipation இருக்கு. Dynamic power dissipation இருக்கு, it occurs during switching transients, that is 1 to 0 and 0 to 1 transitions. Okay, it occurs during switching transients. And as I told you earlier, here we have more area. So that's all about your differential cascade voltage switch logic. So likewise, designing gates as well as Boolean logics, both are possible. Okay, so the only advantage or the only uh, reason behind this, purpose behind this is you can go for obtaining both true as well as complementary output.